Okay, we're continuing our problem solving, and we got a 2D kinematic example here. Mike the motorcycle man. Okay? So he's going off the edge of a cliff. It's very flat. So he's going to have an initial horizontal speed. But that'll change a bit when gravity takes over. So he'll start having vertical speed and horizontal speed at the same time. So he'll travel off that cliff kind of like in a parabola. It'll be a parabolic path as he reaches the bottom, which is going to be like the ground below the edge of the cliff. Okay, so my drawing skills aren't that great, but that's supposed to be a motorcycle and a little stick figure man. And so he'll have a horizontal velocity, it says there 14 meters per second at the height of the cliff. That's also another given. Another given is actually the acceleration due to gravity, which is always there. We're going to assume that this problem's happening on planet Earth. And so that'll be 9.8 meters per second squared in the downward direction. Okay, so that's kind of a rough sketch of the path he'll travel on. In the picture, though, I'm going to actually signify some of my givens and write down the variables. We're solving for this horizontal distance from the base of the cliff to where the motorcycle would land with the man on it. Okay, that's what we're solving for. So I'm doing that in red. That's our target, horizontal distance. So x for horizontal things, so dx for a horizontal distance from the base of the cliff, dx. That's actually going to be measured in meters, even though I didn't really state that. Okay, so that was kind of important. We're supposed to state our units with what we're solving for. Okay, we also have dy, which is the height of the cliff. That's going to be the distance that the motorcycle travels along the y-axis or vertical axis. That was given though, and so we'll put that in a chart where we put all our numbers. Over here it looks like I'm going to go ahead and put a value on there. Don't have to, but 14 meters per second is the initial speed, which is a completely horizontal speed leaving the edge of the cliff. Okay, we're going to get into what we call a t-chart because there's a chart that has like the letter T kind of separating the x and y variables. We're going to use our kinematic equations as we've done before, which has distance, acceleration, time, right? But velocity, initial and final. Okay, but we're going to do it in 2 dimensions. And also in those 2 dimensions, it's important to define which way is positive, which way is negative. So to the right is going to be plus, to the left is going to be minus, and oftentimes downward is going to be negative, which kind of makes sense, pulling down being a negative thing. But it doesn't matter. In this case, we can make down positive. So 9.8 meters per second squared would be progressing downward, would be considered a plus thing. Okay, so that's fine. We can do that, make up negative and the downward direction positive. Anything downward is going to be a positive number. We have x, y, and so this is where we're going to put all of our numerical givens. Okay, we're going to have distances that are horizontal and vertical, acceleration, horizontal, vertical. Time actually doesn't have a dimension, and that'll be the same on both axes, but we'll just go ahead and make a table with 2 columns for time as well. So original velocity or VO will be initial speed. Regular V, I learned that as regular V is actually the final speed, even though it's just a plain looking V. VF is great. You can put like a subscript for F for the final velocity. That helps you think it through. I just tend to be lazy. I know it's not the original, so it's the final. And average, usually I put the hyphen over the V, or I put the little abbreviation for average. Okay, so those are our givens in our 2 axes. It's 2-dimensional. So in the y, looks like we have a distance of 19.6 meters. That was a given, and so that's what dy is signified as, and it's right there in the table. Dx is the unknown. So I'm going to go ahead and put that red. So even if we put the red question mark right in the what we have as the little T chart or T table we have here, that's good. Then that's what our target is. So that's a good way that states your question or problem just fine. But I kind of put it in the picture as well, just to accentuate it a little more. That 0 for A, or acceleration on the x, that means that there's no speeding up and slowing down on the x-axis. But there's gravity on the y-axis, so we have 9.8 meters per second squared there. Okay, so unless there's a force, if we had air resistance, maybe the acceleration would be a negative number. But if we're going to ignore that, it can be 0. We have our initial velocity in the x, which is horizontal, is 14 meters per second. Now there's no acceleration in the x. So that means there's no change in velocity over time. So the final speed right before the motorcycle hits the ground is 14 meters per second. It's horizontally. It's progressing horizontally 14 meters per second the whole time it's in the air until it hits the ground, in which case things might change. Okay. Now in the y, initially it doesn't have any speed up or down, but at the end of the day it'll have velocity because gravity's working on it. But we don't know what that value of speed is in the vertical at the very end when he's reaching the bottom towards the ground. Now we can try equations because that's the next part of the problem solving steps. We've listed our givens, we've drawn a picture, we know what our target question, what it's asking for. Now in the horizontal we could try some of our kinematic equations, like VAD, final velocity squared equals initial velocity squared plus 2AD, or 2 times acceleration times distance. What's really happening there? Well, in the x there's no acceleration, right? He's not speeding up or slowing down. And we know that the final initial speed is 14. So since a is 0, basically we have 14 squared is equal to 14 squared when we plug it in, right? 14 squared equals 14 squared plus 0. We don't really solve for anything new there. So that equation is not really that useful to us using VAD in the x. So, okay, that was fun, but that didn't help us solve anything. Okay, so we're going to try something else in the x. And that makes sense. Let's try the x, right? I mean, what we're looking for is distance in the x, so let's use an x equation, right? See where it goes. We're going to have to use an x equation at some point. So that makes sense there. So I always put the x, and then I know that that is what I'm using, that the kinematic equations along that axis. So here we're trying VAT equation, v equals v original plus at. That's a good one. I'll shoot on something here. Acceleration is still 0 in the x. So now we have like 14 meters per second is equal to 14 meters per second. Didn't solve for anything new. That's yummy. I'm chewing something yummy. I should take a break. You guys eat when you work at all? Because I am. Okay, so we have dat equation is another big kinematic equation. This is one of the last ones we proved. Was it? I think it was. But distance is equal to 1/2 acceleration and then time squared plus the initial velocity multiplied by time. Now when we think about that, when we're working in the x-axis, once again there's no acceleration, so that part's going to go away. Because acceleration is 0, anything multiplied by 0 is 0. So what we ultimately have is distance equals horizontal velocity times time. Or distance equals rate times time. Yeah, that makes sense. For any non-accelerating body, distance is equal to constant speed times time. Distance equals rate times time. So dx is equal to your horizontal or x velocity times time. Now we do have that horizontal velocity as 14. And so we could find our horizontal distance if we knew the horizontal velocity and the time. But we only have one thing, the velocity. We don't have time yet. What could we do? Well, we could solve for time. We've exhausted 3 of the kinematic equations in the x. We should try those maybe for the y. Because for the most part, those 3 kinematic equations should cover almost everything. I think there's one more, like average velocity, we could try. But that's not going to really help us in the x for time, unless we knew the distance. And that's what's missing. That's what we're solving for. So let's look in the y. It seems like that equation was helpful in the x, so I'm going to go ahead and try that in the y. Just so happens that's going to work right away. We could try the other ones and see where those work out, but they won't tell us much either. Mostly because of the initial speed. I mean, we could solve for final speed, I think, doing it bad. But anyway, the initial speed is 0 in the y because it's, right, it's up and down. It's not accelerating up or down to begin with. I mean, to begin with, it's got no velocity. But we do have the acceleration due to gravity, so the distance it travels is 19.6 meters from that initial position downward. Downward's plus, so we make it a positive sign. Acceleration's down, so that's also a positive sign because that's how we define it. Down is positive. So this works by the way we defined our variables. It could also both be negative, and I think it would have worked out, right? Because it would kind of canceled on both sides. Solving for time here, basically, we got 19.6, right, times 2 divided by 9.8. Yeah, basically we're going to get 4 is equal to t squared. And then what's the square root of 2, guys? So we'll see that carried out. And once we have time for the thing to fall straight down, but the time for the motorcycle to fall down is also the same amount of time that passes as the motorcycle goes from left to right. So that time value is good on the x or the y side of the data table of our givens. So our t-chart has 2 seconds or 2.0 seconds for x or y. Time is just there. It's not really different in the x or the y. Yummy. Okay, you can see where this is going. Now I've got the time that it took for the motorcycle to travel left to right. And we've got the speed. So rate times time, 14 times 2. Hey, we're almost done. We're going to have 28. Now let's go ahead and look at our units, because I've been it's been poor form. I haven't showed my units this whole calculation. And you can show your units for the whole calculation, and it's probably the ideal way to do things. Let's see that meters per second is the unit for velocity, times seconds, so the seconds cancel, and we get dx is 28, and we must see that the units are meters, and it's a distance unit. So that works, and we should always box our final answer. I'm going to show you a short simulation here of how it should work. There are simulations online. This is another program it's an older program. I'm not sure how much longer it's going to work on our new machines, but you see we got the height of about 19.6. We've got the acceleration due to gravity is negative 9. So downward is considered negative in this case. And then we see the path. We're at 14 meters per second. And we can see that that's almost 30 or 28 meters right there. So the simulation shows the path that it would go on. So that worked out. You can always look at that again. But looks like we've done a good job, and that's all the problem solving steps and our correct answer. Yay, alright.